so we're in the second week. Time has gone on. We don't have a black and white picture. We have a color picture. Anyone? Who is this? Not a geodesist, actually, a geologist. As you might guess from the quote, which is something that I can't completely stand behind, but this is George Plafker. And what you see here is some of George's work from the 1964 Alaska earthquake. So he made measurements. Basically, he was doing geodesy as a geologist. He was just using a tape measure and sea level as his measure, but showed that there was this pattern of subsidence and uplift. This is just a thing in cross-section caused by the 1964 earthquake. And at the time in 1964, the leading seismologist of the day, who is not shown because he was wrong, Frank Press, or one of the leading seismologists, anyway, there was the focal mechanism for this earthquake showed either a nearly horizontal plane or a nearly vertical plane. And at least in his science paper, Frank Press argued for the nearly vertical plane. These data and the simple sort of model you get from it showed that it was the horizontal plane, or the nearly horizontal plane. Today we would just call this the megathrust, but in 1964, it's pre-plate tectonics, it was a little bit more controversial. So what you observed was this dramatic uplift out towards the trench, and then this band of subsidence inward. And so again, before we had really, really precise instrumental geodesy, we had measurements relative to sea level. Okay, so some of the related lectures, this is no longer Whitney, this is now going to be Uli. There's actually another rheology, so we have lots of rheology you'll be hearing about. On Wednesday, Susan Schwartz is going to talk about megathrust earthquakes from a seismological perspective. So there'll be a lot of complementarity between our two talks. And then Matt Pritchard and I have a deformation tutorial on Wednesday afternoon. And on Saturday, Matt is talking about volcano deformation. So I won't touch INSAR or volcanoes in this lecture because Matt is going to cover those on Saturday. Okay, I'd like to start by making sure you're awake. So this is for the students and the postdocs. What do you see in these data? And before you answer, let me just first tell you what these arrows mean. The arrow shows the rate and direction of motion of a point on the ground. So we're looking at basically how the Earth is moving and deforming. So what are the first order features that you see in these data? Okay, everybody's asleep. Come on, wake up. Rotation, yes. There is a very prominent rotation that you see in here. In fact, the vectors get a little larger as you get closer to the coast, but they're certainly rotating pretty dramatically in a clockwise fashion. What else do you see in the data? Well, let's look at the next one. So I'll show you now just a blow-up of Northern Oregon and Washington. So it's the same vectors, just plotted a little bit differently. The rotation is not as clear because we're looking at just the coastal part. But what do we see here in the coastal area?
Faster velocities near the coast.
Yes, faster near the coast. So the sites here on the Pacific coast move faster and then slower as you move inward. Okay, so that means there's a contraction, not just across the forearc. The arc is somewhere over here. It's actually across the whole part of the upper plate. We see this contraction in the data. And actually, we can see a little bit of a hint of the rotation. Did I skip one? No. A little bit of a hint of the rotation. Now, I'm gonna subtract something from the data. I'm gonna subtract the rotation from the data. So we'll have a model that would explain this rotation. If we subtract that from the data, this is what we get now. So if we just compare these two, you can see what's changing. The orientation is changing. You may or may not be able to see there's a rotation that you can still see inland here. But when I've subtracted that out, whoops, it's gone. So now everything is moving in the same direction, basically, within a little bit of noise. And that's more or less the Juan de Fuca plate subduction direction. So that's the rate of direction of relative plate motion. And we see this contraction across the upper plate. Okay, and that's what I subtracted out. That's the rotation component that I subtracted out. I forgot to mention, but all of these, the data and models that I'm showing here in this particular example, all come from a paper by Rob McCaffrey a few years ago. Okay, what about this? What do you see in these data? It is an earthquake, that's correct. It is, in fact, the 2011 Tohoku earthquake. This figure came from GSI, the Geospatial Authority of Japan. They made it the day after the earthquake, so that's one reason why the magnitude is a little bit off. Yeah, more specifically, what do we see in these data? Which way is everything moving? Towards the coast. Everything is moving seaward. That's opposite in direction to what we saw in the previous figure. Everything is moving seaward. What else can you say about those vectors? Comparing east coast to west coast of Japan, for example? What's the sense of strain across the upper plate? Extension. Yes, somebody said extension. The whole upper plate here is an extension. So everything is moving seaward as a result of the earthquake, and the upper plate is put into extension. And there are some nice little rotational things that you actually see in a couple places. For example, there's a rotation of vectors here and a rotation of vectors there. Actually, what those are telling about is about the lateral extent of the earthquake rupture. So with a little bit of experience, you could actually basically draw the length of the rupture just by looking at this figure. And of course, an inversion could do it very easily. So again, this is what we saw in between earthquakes. So this is data from a decade or two from Cascadia when no earthquakes occurred. We see this contraction. And what we've basically seen here is how the subduction zone megathrust cycle, earthquake cycle, appears in ground deformation. We saw this contraction across the upper plate between earthquakes and an extension across the upper plate during the earthquake. So those two are opposite in sign, and we think over the long term, if you average over an entire earthquake cycle, approximately equal in magnitude. We also saw motion and deformation of the upper plate. In fact, most subduction zones are part of deforming plate boundary zones. So we like to draw these simple 2D cross sections with an undeforming upper plate. And the motion of the upper plate, as you saw, that rotational motion it wasn't in the subduction direction. It was actually almost orthogonal to the subduction direction. But the subduction zones are almost always part of deforming plate boundary zones. Sometimes it's a matter of motion of upper plate blocks like we saw in Cascadia. Sometimes it's a matter of slip partitioning of oblique subduction. But in general, the upper plate is deforming. Okay, so I'm going to tell you very briefly about GPS, or what's also called GNSS measurements. This is Global Navigation Satellite Systems. So it's just a more general term. GPS is a GNSS. But within a few years, everybody is going to be using multiple satellite systems to get basically better results than we can get today. I'll talk about how plate motion is accommodated at subduction zones, go over a simple physical model for megathrust slip, talk about earthquakes, slow slip events, post-seismic deformation. If I have enough time, I'll get to this last topic, which would be essentially non-megathrust deformation, the surface deformation that actually comes from earthquakes in the downgoing plate. So we'll see if there's time for that or not. Okay, so first of all, GPS measurements. We make these measurements by having a GPS receiver. This is actually the antenna. The receiver is just a little box, but the antenna sits directly over, in this case, some point on the ground. So here you can see a little silvery thing, which is a marker that's been attached to this rock. We put the antenna directly over it with a known height or a measured height, and basically we're going to measure the position of this antenna with GPS and relate it to the position of this marker on the ground. This is an example of a continuous GPS instrument. The antenna is actually contained inside this gray radome, so that's just a piece of plastic to keep stuff out of the antenna. Basically the whole thing is mounted fairly rigidly into this rock using, in this case, it's not a tripodal structure, it's kind of a quadru or pentapodal structure. But anyway, the idea here is to have something so that the antenna is fixed in a highly rigid manner to the ground, so that we're measuring the motion of the ground, not the wiggling of an antenna or something like that. So the way GPS positioning works fundamentally is by measuring distances between satellites and receivers. So here's a picture here. You can see little indications of where the radio waves would travel. You measure distance by measuring time and using electromagnetic radiation as your method. So the GPS satellites emit signals that have some distinctive character to them, and you can measure the travel time, how long it takes to get from there to here. And so if you have perfect measurements, and you had 3 satellites and you measured the distance to each one, you could determine the position of your receiver on the ground, whatever it may be, whether it's the car or the plane or something else. Now, for tectonic purposes, we're doing positioning at the millimeter level, roughly. So if you want to do millimeter level positioning, you need to measure those distances with a precision and accuracy of a millimeter. So who can tell me how long does it take light to travel 1 millimeter? Order of magnitude is okay. Excuse me?
10 to the minus 11?
Close. It's actually 3 times 10 to the minus 13 seconds. So if we want to make millimeter level measurements of this distance, all we need to do is have clocks that are accurate to 10 to the minus 13 seconds and synchronized 10 to the minus 13 seconds, and have some of them be in space and some of them be on a moving platform or maybe something that you could put in your pocket. Okay, that's actually a few orders of magnitude beyond what is possible. You can't do that. There is a way around that, and the first thing you could do is if you actually had 4 satellites instead of 3, the receiver, whatever its clock error is, it biases all measurements equally. And so if you had 4 satellites instead of 3, you could estimate position and clock error, and then you don't need a super expensive clock in your receiver. You can use something that is affordable and could work. Even what's in your cell phone or your watch is good enough for that. But that still doesn't get you around the need to have like 10 to the minus 13 second accuracy in space, which is still a couple of orders of magnitude beyond what is feasible. And the way we get around that is by going differential. So what we recognize is if we have, for example, this tower recording GPS signals and this tractor recording GPS signals, the satellite clock error here biases both of those measurements equally. And so if we make a differential, for example, we could just difference the data between these 2 receivers, and that difference removes the satellite clock error. Alternatively, we could take a bunch of receivers and estimate the satellite clock errors, but fundamentally it works out to be the same. So we get around the need for this impossible accuracy of clocks by doing differential measurements. And so what we're actually going to measure is not the position of the tractor, it's going to be the position of the tractor relative to the tower. But we can do that actually, if we model a lot of other things, we can do that at millimeter accuracy. And so we'll do that not with a tower and a tractor, but with a global network of GPS sites. So this is a small fraction of what is available around the world. Again, the idea is we're going to measure the vectors in 3D between all possible pairs of these receivers. So again, we measure position by measuring distances to satellites. That allows a few satellites to serve an unlimited number of users on the ground. The high precision GPS, I'm leaving out a lot of details. I'm even going to tell you at the bottom, even then I'm leaving out a lot of details. We're actually going to use the phase of the carrier signal. So basically a phase of an underlying sine wave that is broadcast to measure change in distance over time. We need to know satellite orbits. We have a lot of things we have to deal with, but one that is a persistent sort of error source is the atmospheric path delay. So that is basically accounting for the difference between the speed of light in a vacuum and the speed of light in the atmosphere. As I said, I'm leaving out a lot of details, probably about 100,000 lines of code of details. So you have to actually model a lot of things very precisely and accurately to get down to that millimeter level, but it's been very well established now that we can do it, and it's fairly straightforward for the user. So again, we take our global set of GPS sites, get rid of the unnecessary things and get down to what's important, which is where the GPS sites are. And we can construct, essentially, when we have a network of GPS sites, we're sampling the shape of the Earth at potentially a large number of locations. And every day, we're going to determine the relative positions of all of these GPS receivers. So if we do that on a daily basis, we are effectively measuring the shape of the Earth on a daily basis. As I mentioned, these are all differential measurements. We actually don't completely lose our ability to do absolute positioning, but it's way less accurate than the differential measurements. And so effectively, we know the shape of this figure defined by all the GPS sites, but we don't know its position in space at the same level of accuracy, and we don't know its orientation at the same level of accuracy. That is, you could take the whole figure and rotate it a little bit, and in the process, you would sort of rotate your satellite orbits a little bit. Everything would fit the data about equally well. So we have to actually apply some external information about a small number of parameters that define the reference system. Essentially, we have to decide the origin and the orientation of the axes and the scale. So, and how those things change with time. So that comes through an external reference frame, which we call ITRF, the International Terrestrial Reference Frame. If we do that and take then positions every day, we can, in many cases, turn those into estimates of motion. So these vectors then are just showing the rate and direction of motion of the particular set of sites that I showed you here. This is the North American plate. You can see the rotation of the North American plate. So this ITRF is a very, very precisely and self-consistently defined reference system, but it doesn't have any geological meaning by itself. It's not fixed to any plate. It's more or less a no-net rotation, overall rotation constraint. But if you want to do geology with this, you need to look at things relative to a plate, for example, by subtracting out the rotation of the North American plate. Okay, we also spend a lot of time looking at time series. These are the data that go into those velocity fits. These are a couple of sites in Alaska. This is off of the Alaska Peninsula, so it's out over the subduction zone. This is in southeast Alaska. Each little dot, which you can in some cases see, is a daily measurement of the position. This is the latitude or north component of motion, the longitude or east, and the height component of motion. The scales are actually different in the two plots, so don't worry too much about it, although I did put, in this case, which is very linear in time, I did put the rates of motion. But what you can see is sort of the scatter. In this case, you can see the east scatter is about 3 millimeters about the best fit line. And the same is more or less true over here for this site. This one actually has an interesting signal you can see in the vertical. There's a sinusoidal annual period signal. That's actually the deformation of the Earth due to the accumulation and melt of snow. And in fact, the reason that this site is popping up rather rapidly, it's a 20 millimeter per year uplift rate. That is a combination of present day melting and the last couple hundred years of ice loss in southeast Alaska. So there are some non-tectonic things that can play a pretty large role in what we measure in some cases, and we have to be careful if we're interested in tectonics or earthquake cycle that we don't get confused by something that's also got glacial isostatic adjustment or volcanic deformation in it. Here's an example of an earthquake. This is a site from Mizusawa, which is in northern Japan, and there was actually a moderate earthquake in 2008. That's that little step. This big step is the Tohoku earthquake, and then you can see this beautiful nonlinear relaxation process that followed the earthquake. That's post-seismic deformation. It actually follows pretty close to an exponential decay, and I'll talk about that a little bit later in the lecture. Okay, so how precise is GPS? Yes?
Why does the first earthquake go in the opposite direction?
Okay, so the Tohoku, of course, is a subduction earthquake. This was actually not a subduction earthquake. It was an earthquake well, it was on land, essentially. And so the reason for the difference in sign is just the different position of the site relative to the earthquake in those cases. Did we have another, any other questions? Yeah, Doug.
Well, I just had a question about the positional accuracy of GPS, which I think you were just getting to. Does that depend on how far away you are from one of these reference GPS sites? So like if you're at on an isolated island in the middle of the Pacific, right, then do you have less resolution?
So it doesn't matter anymore. If you go back in time, it did matter. The difference has to do with the quality of the GPS orbits. So, so if the orbits are not so good, then you're going to get an error that will grow with distance. These days, the orbits are actually known at about the centimeter level. So the satellite, after the high precision orbits that we get give us the position of the satellite at about a 1 to 2 centimeter level. And that amounts to essentially a negligible, almost negligible distance error. So more or less, the length of the vector almost doesn't matter. There's a little bit of a sensitivity there. Really, really short ones, you can ignore some things that you have to estimate normally and get a slightly more precise result, but there's not a strong dependence anymore on the separation between the sites. So effectively, what we can, okay, come on. Let's get back to where we were. Yes, effectively what we can look at is something like 1 to 2 millimeter horizontal and about 3 to 6 millimeter vertical globally. That is the white noise component, or the uncorrelated noise component. There is also a time-correlated noise in every GPS time series, and this comes partly from the atmosphere, from the fact that our models aren't perfect for removing it, and the fact that, well, particularly here in Berkeley, it seems, the weather is highly correlated from day to day, right? But that's true in most places. The weather tomorrow is likely to look a lot like the weather today. So if your model has some error, the error is probably going to be pretty similar tomorrow and today. So there's time-correlated noise on a short time scale that comes mostly from the atmosphere. On a long time scale, it probably comes from mismodeling some things in the orbits. Even though we're doing these 2 centimeter orbits, there's still some systematic little biases. That's a precision measurement. For sudden events like earthquakes, the displacement precision is dominated by white noise. And for velocities, the uncertainties are dominated by the time-correlated noise. So the worst case is velocity error is sort of like 1 over the duration of the measurements. But it's often a bit better than that. If we just simplify for long-term continuous GPS, because there's thousands of those around these days, the precision of relative motions can be as good as approaching a small fraction of a millimeter per year. That is one site relative to another. This is sort of the best case. This assumes that the sites never have any equipment changes, and there's no offsets, and there's no weird nonlinear things going on, and all sorts of things like that. And no birds come and like poop on the antenna, and ice never accumulates. I mean, so it can be worse than that, but that's our best case. The precision of absolute motions is dominated actually by the reference frame error. That is tying that geodetic frame back to the Earth. Depending on who you ask, that error could be as large as, or smaller than 0.5 millimeter per year, or maybe as large as 1 millimeter per year. So actually, again, our measurements are much more precise and accurate in terms of relative motions than they are in terms of absolute motions. And the biggest uncertainty turns out to be along the spin axis, the polar axis. Okay, so let's look at subduction zones. How is plate motion accommodated? We have a variety of things going on. We have block motion on the overriding plate that might be moving in some direction. We have slip on the megathrust. We have deformation in the four-arc wedge, which is something that I don't know we're talking about at all, this part of the subduction zone. We have contraction or extension of the downgoing plate. We have flow in the mantle wedge. If we were to take a whole series of cross-sections and make those cross-sections go deep enough, we should be able to basically account for all of the motion. If we just take for a moment in the four-arc, for example, if 10% of the plate motion is occurring through bulk deformation of the four-arc wedge, then only 90% is occurring by slip on the basal thrust. Whatever the fraction may be, if 10% of the plate motion is being taken up by block motion of the overriding plate, then only about 90% is available for slip on the megathrust. So we should be able to do a slip budget anywhere we like in the subduction zone and come up with where is the plate motion being taken up. Okay, so let's start with deformation of the overriding plate. This figure actually came from Lucy Flesch. The vectors, though, are from Cornet Kramer at University of Nevada, Reno. So North America is put on its side here. And we looked at this rotation already. This actually shows a larger area, and you can see that rotational pattern actually goes all the way back to the Wasatch Front. So it's a large-scale feature. It's actually, yes?
How did you already deconstruct the vectors into these? Can you explain how you deconstructed the observations into these different components?
Oh, in terms of the rotation and...
Well, yeah, in terms of showing us, okay, you're going to show us, the other components, I guess.
Yeah, so this is simply, for all the sites that actually show linear motion with time, this is just the actual motion, what we see. So this is directly the observation for sites that move linearly with time. The rest is interpretation, because when you have this rotational pattern and you have this right lateral shear associated with the San Andreas system and so on, if you want to study one component of that, you have to be careful that you're accounting for the effects of the other ones. And so I'll show you a couple examples of that, but as you already saw in the first example I showed you for Cascadia, the vectors have different orientation and slightly different character with and without that rotational component. So fundamentally, in the end, you often have to estimate all of them together. To really, sometimes you can separate them out. You can separate out one component well enough that you can constrain another one, but often these things are mixed in the observation. So the data that you see here often contain a mixture of your subduction zone related strain, tectonics, volcanism, etc. So they're often all mixed together. Yes?
Is it correct to assume that all this displacement has a reference system?
Yes, I forgot to mention what the reference system for this is. All of these are referenced to the North American plate, or at least to an estimate of the North American plate. And so what you'll see is you can see a bunch of little dots back here. Those are actually sites. And the motion relative to North America is so small, it just looks like a dot. Everywhere that you see something that actually looks like a vector, you've got something on the order of at least a couple millimeters per year relative to North America. So everywhere from the Wasatch to the west, and everywhere through the Canadian Cordillera, and everywhere in Alaska, the motion of the overriding plate is at least a couple of millimeters per year or so, which is a combination of, again, in some places subduction deformation, in some cases it's due to other components as well. This is just another view from an earlier paper by McCaffrey of a block model. So each different little colored area is modeled as a distinct block that is rotating, and this shows the rotational motions of those blocks. These were all estimated from the GPS data along with other parameters, but it gives you some idea of how that rotational motion is accommodated. Different people, of course, will come up with different block models with slightly different boundaries and so on, and then that's a matter of interpretation as to whose model might be better or not. But what I'm just pointing out here is I want you to take away that there's a pervasive deformation of the overriding plate, and that deformation is not entirely driven by the subduction zone, or at least not completely so. That is, this rotation is driven in a large part by shear from the San Andreas system and how that couples with extension in the basin and range. So the subduction zone is embedded within this larger tectonic system, and that has an impact on how things are moving. if we actually just look at blocks, this is each one of these labeled regions is somebody's estimate of a supposedly non-deforming block in a plate boundary zone. The details are you know, some people argue about some of these, but the bottom line is everywhere around the entire North Pacific, the upper plate is deforming. And so that's the part I want you to take away, is there's nowhere here that the upper plate is rigid and non-deforming. It's always getting smushed in some way or another as part of the tectonic processes that are linked ultimately with subduction. That's true actually almost everywhere else. There are very few places where it's not. Here's an example from New Zealand. So these are velocities relative to the Australian plate. Here's North Island. Again, you can see a beautiful rotational pattern in North Island. And all the vectors in South Island are more or less in the same direction, like this. So they just mostly show shear. There's actually a little bit of contraction across the Southern Alps, but mostly what you see is strike-slip motion. There's a subduction zone off here, the Hikurangi Trench, and actually you can't, in this particular data set, without taking out the rotation, even really see the subduction zone strain very clearly. You have to remove the upper plate rotation and estimate that along with the subduction zone strain. So this is in the colors here from a paper by Laura Wallace a number of years ago, an estimate of what is called the slip rate deficit or slip deficit. And that's basically just the difference between the plate motion rate and the slip that's occurring at a steady rate on the interface. So we're basically looking at how much slip is not happening in a short period of time. The reason for doing this kind of an accounting is that ultimately that slip has to be released somehow. And the somehow generally is great earthquakes. So we're essentially looking at how much slip is available or how fast is slip deficit accumulating to be later released in great earthquakes. And basically there's a big patch over here in southern North Island and not much of anything in northern North Island in terms of that. So basically the inference is that most of the plate interface up in northern North Island is creeping at a fairly constant rate close to the plate motion rate, whereas that's not true in the southern part of North Island. And again, to get this sort of thing, you have to effectively estimate that along with the deformation of the overriding plate. Whenever you're estimating multiple parameters, there are trade-offs between those parameters, and you have to be aware of those and cautious about them. Uh-oh. Yeah, hold on, let me see whether, okay. Yes?
Sorry, if you just get rid of the figure that you just put up, on the first bullet you say almost always moving and deforming. Where and when does that almost refer to?
Okay, so I was thinking about places where I didn't see that sort of deformation. I think Java doesn't have substantial deformation of the overriding plate in that things on Java away from the subduction zone are pretty well described as part of a Sunda plate. Of course, it's still part of a plate boundary zone, but Java itself there's not a substantial amount of sort of localized deformation, whereas in Sumatra, of course, there is. It's very well known. There may be a few other places, but there's a small number of places where you don't see a substantial. Even in the Andes, there are these slivers moving things laterally, parallel to the arc. So pretty much everywhere you do see that motion. Yes, Jim.
So Jeff, when you do that accounting, for say some kind of tectonic deformation, do you explicitly have to actually do, say, a block model and forward model it, or can you decompose that directly from the data? You
can't really decompose it directly from the data. You have to do some kind of a fairly explicit model. There are in these relatively complicated cases, which most of them are, you pretty much have to make some assumptions about, for example, in New Zealand, these faults are strike-slip faults. They're well established. And so the assumption is most of the motion is occurring on those strike-slip faults, and we know that they're dominantly strike-slip. And so, so that gives us a fair amount of constraints that can be used in doing that. But yeah, you can't, in most cases, you can't get it very easily out of the data. There's a few examples where you can, but not very many. Yeah, Torsten.
Just a comment that block model is often used in different ways.
Yeah.
And the simplest, I guess, is it's a rigid block motion, where the model is a very simple one. It's still a model, but it's a fit to a rigid, thing on a sphere. But then there are block models which will take into account the locking on faults and the interactions between faults, and those are also often referred to as block models. So they're, you can use them to do the same thing, but they're different levels of abstraction, I guess. Yeah,
exactly. So what Torsten was pointing out is, and I haven't really talked about this yet, but in a case like this, if you, everywhere that you have a fault that is not creeping at a constant rate, if the shallow part of the fault is actually stuck by friction, there will be deformation around the fault that is resulting from that. It's actually, I'll show you what that looks like for the megathrust in a few minutes. But if you don't account for that, you're guaranteed to get the block motions wrong. So you have to account for that, and except for places where the sites are very, very far away from the faults, you always have to account not only for the block motion, but also for the elastic deformation that results from the block bounding faults. So that's pretty much always something you have to account for. This is a picture of what what Laura estimated the subduction strain component looks like. So these are the velocities that result from the megathrust being locked. And the other part of the velocity field results from the rotation. So you sum those two, that up with the rotation, you get the data. Whether that's correct or not depends on really whether she did the block model correctly, whether she made the right assumptions, and in fact, whether those blocks are rigid and non-deforming. They might not be. At some level, they're not. So, so these are the kinds of things that go into the more detailed modeling. Whoops. How did we go to class 2? Okay. So let's now stick to the, or go to the earthquake cycle. So a simple earthquake cycle model, and this could be true for any fault, is ultimately based on an analog of a one-dimensional spring slider. So this is a block, like a heavy brick. If you put a heavy brick on the carpet and attached a bungee cord to it, and then you just started walking and extending the bungee cord, elastic energy is being stored up in the bungee cord. The elastic, the force exerted by the bungee cord on the brick is getting larger and larger. Until that force is larger than the force of friction, the brick doesn't move. As soon as that is larger than the force of friction, the brick starts to move. And so that brick starting to move is the earthquake cycle. So this gives us basically two modes, something that happens between earthquakes, where tectonic forces are basically in a sense, storing up elastic energy to power earthquakes. So what we see is that between earthquakes, that interseismic period, the shallow part of the fault is locked. That is, friction keeps the two sides stuck together. Eventually, of course, shear stress gets large enough that it exceeds friction and the fault then moves. But the deeper fault behaves differently. The deeper fault seems to creep at close to the long-term slip rate. And that's partly a rheological difference. Some of that is a change in friction, and Susan is actually going to talk more about friction in a little more depth than I will. Some of that ultimately at lower crustal depths involves permanent shear of the rocks. During the earthquake, the shallow fault slips. So again, the simple model just has these two phases: stress builds up, earthquake occurs, stress builds up, earthquake occurs, and so on. That would be fine if the Earth was elastic, but the Earth, of course, is not quite elastic. So it's a simple approximation. When we turn that for the subduction zone, we get to have a few extra interesting complications. So here is our subduction zone. What we tend to observe is that most slip in earthquakes occurs within some particular depth range. Sometimes, like in Tohoku, the slip actually goes almost out to the trench. and sometimes it goes out and comes up a splay fault. That happened in 1964 in Alaska. Sometimes it just happens at depth and doesn't rupture the shallow part at all. There's a depth limit, which varies a little bit from place to place, and I think Susan may be talking about this in more detail. We actually get more constraints sometimes on the depth limit from earthquakes, where thrust earthquakes occur. But in a lot of places, between 25 and 30 kilometers depth is sort of the deepest major slip we get in big thrust events. And deeper than that, we see these slow slip events, or episodic tremor in slip events, as they've been called in Cascadia. And then deeper on, we don't see deformation coming from this deeper part of the interface when you start to get, even when you get into lithospheric mantle probably. So at some point, we're no longer seeing strain that's coming from something that looks like a locked fault at all. So we have to be counting for slip that occurs as creep, steady creep, transient creep, and then sudden seismic slip. Okay, so this is a classic picture of the megathrust seismogenic zone at the shallow end. The idea is that the main seismogenic zone has big earthquakes because of its frictional properties. So the type of friction is such that it generates essentially unstable slip. And what that has to do with is whether the dynamic friction is greater than or less than the static friction. If you have a case where the dynamic friction is smaller than the static friction, then once it starts sliding, friction goes down, which means the force goes up, or at least the frictional force goes down. The driving force doesn't necessarily change that rapidly. So if the friction force goes down faster than the driving force goes down, you get acceleration. So, so if the dynamic friction is lower than static friction, you tend to get unstable slip, although that does depend on the time scales of those evolutions. And then ultimately, if the dynamic friction goes up as the slip rate increases, you could have actually stable sliding. Frictionally mediated stable sliding. So the idea is that we've got a mix of these sort of unstable, conditionally stable, and stable sliding regimes. And where this comes from is, first of all, the observation of seismic asperities, geodetic inferences of creeping and lock behavior, and ultimately the rate and state friction model. And so Susan's going to talk a bit more about these, but what I want to point out is that actually there's a lot of variation. Even if this picture might apply to one place, another place might look a little bit different. Some of the complications, shallow near trench area may or may not be locked and may or may not slip seismically. And also these stable, unstable transitions vary along strike. They can occur at different depths in different places. And actually, you saw that in New Zealand. There was an area where the whole interface practically was creeping, and then an area where a large part of the interface was locked. The temperature of that locked to creeping transition is completely different in those two places. So it's not a temperature-controlled phenomenon. It's controlled by something else, which we actually don't fully understand. If we look a little bit deeper, we have to deal with the fact that this is all embedded. Well, first of all, the down dip transition from the locked region is dynamic. We get these things called slow slip events, and I'll talk about them, and Susan will as well. We also have this megathrust is embedded in a three-dimensional medium that has various properties. Parts of it may be elastic, parts are viscoelastic. So we have to actually account for the response of the asthenosphere to stress changes caused by earthquakes and steady motions. All right, so let's look at how we calculate the deformation at a subduction zone. So here we have, this is just a plane intended to be a plane on the surface, and this is a fault. So we typically model this by embedding a fault as a dislocation in an elastic or potentially viscoelastic medium, most commonly elastic. Come on. Okay, there we go. This is an example. Again, you can see little arrows. You may be able to see the error ellipses or heads arrowheads at the end. This is a particular example. This is a relatively steeply dipping thrust fault. And so the pattern of displacements is a little bit non-intuitive. This is actually going this way, and that's actually going that way, on the other hand. But in any case, it's actually a fairly simple analytical solution if you're dealing with an uniform elastic medium, and a tractable numerical solution if you're dealing with a complicated, more complicated and realistic medium. Okay, now it goes twice. Why did it go twice? All right, so let's look now at this in cross-section, and we'll look at a simpler case, or at least one that's a little more intuitive to me, which is the shallow dipping thrust. So this is more typical of the megathrust at a subduction zone. So our model here at the bottom, this is distance from the trench in kilometers, so the trench is actually off the figure to the left. The red is the locked region, and then below that, the megathrust is creeping. So we're going to take this kinematic specification of plate motion, creep at plate motion rate here, and zero creep in the locked region, and calculate what the surface deformation would be for that. And Jim Savage showed us how to do that. The basic idea is that you use superposition. An elastic system is a linear system, so you can break your slip down into as many components as you want, calculate the response to each component, add them up, and you get the response to the total thing. So what Savage said is, first of all, take a model for steady creep over the entire interface at the plate motion rate. What's the deformation due to that? And he argued that for the subduction case, if you're interested in what's happening on the overriding plate, if the downgoing plate is just sliding smoothly past, you wouldn't expect any deformation at the surface on the overriding plate. That's true for an elastic medium. It's not quite true for a viscoelastic medium, but it's true for an elastic medium. And so that's one component. And then if you put backwards slip on the locked part, then the sum of slip, positive and negative, is zero. That gives you zero slip here. And you calculate the deformation using a dislocation model for that backward slip, and what you get is a curve that looks like this for the horizontal motion. So the particular parameters are more or less through the Kenai Peninsula of Alaska. The red is the horizontal motion, this is the trench normal velocity, and then this is the vertical velocity that you would get out of this model. So the vertical has an uplift peak centered basically over the locked to creeping transition, and out over the locked zone you get subsidence. And we observe this subsidence in places like Costa Rica and Sumatra. In between earthquakes, we actually see it in a couple places in Alaska as well. So we can really see that. And the sites close to the trench or close to the coast are going to have a large horizontal velocity in the direction of plate motion, and that gets smaller as you go inland. So that's that contraction that we observed right at the beginning of the lecture. It comes exactly from the locked megathrust. You'll see there's a little kink here. That kink is an artifact, essentially, of the fact that we went from completely locked to completely creeping abruptly. If you simply make that a gradual transition, the kink disappears and it becomes smooth. So we don't actually know exactly how sharp that boundary is in most cases, but often we'll model it in simple ways that produce things like that little kink. So that gives us a way of actually calculating this. If we now look at how does the Earth deviate from the simple model we're looking at, I mentioned already that there are along strike variations, so the extent of slip deficit varies along strike. There are slow slip events and transient slips. These are mostly down at the down dip end of the seismogenic zone. We see post-seismic deformation, and again, a common theme is slip on the interface varies with space and time. So not just interseismic and coseismic, and you can't break an entire subduction zone down to a single cross-section. So here's an example of what a long strike variation might look like. This is a forward model. So we have the trench out here in red. We have a large locked area and a smaller locked area. And then these are the predicted motions. This is the relative plate motion of the downgoing plate. And then we have actually a gap in the middle where we don't have any locked region at all. So this actually kind of looks like the 1964 earthquake region, again, modeling things after my favorite spot. Anyway, if you just pick any distance away from the trench, what you'll see is the vectors here are smaller than the ones over there on a systematic basis, and the vectors in the middle are smaller than either side. You can look at the contraction across the region. The contraction is smaller here than it is there. So those basic measurements of how fast are things moving inland and how much contractional strain is there tell us about how wide the region that's locked actually is. And also can tell us if there isn't a locked region. So to first order, we can figure out what is locked on the interface by taking data and doing an inversion to go backwards. And the way we would do that inversion is every geophysicist will probably include this equation in their talk in some form. But D is the data. So these are the observations. And we're going to explain the observations with a linear model relating a set of model parameters M, which might be slip rate, for example, on one of the faults. So the way we calculate that is we could take, let's take one of these rectangles, for example, this one. We would put unit slip on this rectangle and predict how all of our sites would move. And when we do that, that is going to give us a column of G. And we repeat that for all of the other rectangles, however many we might have in our problem, and that gives us our linear model of how each site would move in response to unit slip on each model parameter. Once we have that, it's simply a matter of inverting this system of equations to come up with the best model parameters that fit the data. So I'm going to leave the rest of the math because if you're not a geophysicist, you probably don't want to know. But it's actually not that hard. This particular system is a little bit different than the one that you played with the tomography, because this is, if the number of model planes is small, this is an overdetermined system. We can use standard least squares. If the number of model planes is large, we have some parameters that are well determined and some that are very poorly determined. So it's a little bit different than tomography, which is, generally speaking, has more parameters than data. We can actually parameterize this in that way, but and in that case, we have to do something similar to what the seismologists do for tomography. Okay, so if we do that, this is about a 10-year-old result from Alaska. These purple patches are where we infer the subduction zone to be locked. The dark ones are estimated from GPS. The light purple are just earthquake asperities, so repeating large earthquakes. The question marks means we have no idea whatsoever what's happening there. And then these yellow regions are places where we infer that most of the plate interface is creeping. So we simply do not see the strain from that, and I'll show you an example from this region. So this is Alaska Peninsula. So again, we're looking at here. These are the observations. This is work that's in progress. We should be getting this written up this year. But all of the green vectors are observations. The red are the vertical velocities. So you can see out here, you get some rather large vertical subsidence. And this is a scale, 2 centimeters per year for scale. So the plate motion rate is about 6 centimeters per year approximately here, and this is what we see. So for example, here, nothing is moving in the plate motion direction. There, everything is moving in the plate motion direction. Okay, so I made a small correction for 1964 post-seismic deformation and glacial isostatic adjustment. It doesn't make that much difference. And now what I'm showing in these little gray vectors are our estimate for the motion of this block relative to the overriding plate. And that actually comes not only from the data here, it also incorporates some additional data from farther out the Aleutian arc. And if we subtract that block motion, then we see everything moves basically in the direction of the Pacific plate motion. Everywhere we see larger vectors near the coast, and they get smaller as you go inland. There's a little deviation here. That's because that's a volcano, and there's some volcanic deformation. But largely speaking, everything now is moving in the direction of plate motion, and we can see that these are actually rather different. So if you take a look at these sites here, they're much, much faster than these over here, even at the same distance away from the trench. So whatever distance you're looking at, whether it's along the Pacific coast or at this sort of distance from the trench, these vectors are substantially smaller than those, which basically tells you that the plate interface locked part is wider up at the northeast end than it is here. And these, when we subtract out the block motion, are essentially 0. In fact, the best fitting strain here in the plate motion direction is 0. So that would basically suggest no part of the plate interface offshore is locked. Or if it is, it's way out by the trench, far enough away that it doesn't really impact our data. Okay, and if we come up with a model to explain the data, the color coding is basically fraction of plate motion slip deficit. So the red area means there's a wide locked region that becomes progressively narrower as you go along the margin, until finally you get over here and you have basically 0. And so there's some residuals shown here. They're relatively small. This is the model in blue and the observations in red. So more or less we're fitting the data. It turns out that what's interesting is this data set actually prefers sharp boundaries along strike. So, so it's fine to have a smooth boundary between locked and creeping in the down dip direction, but the model actually fits better with sharper boundaries in the along strike direction rather than smooth boundaries. And we tested that by just taking a sharp boundary and widening it and comparing it to the data. And it's actually overall a better fit if we go with a sharp boundary. So there's these big along strike variations. They seem to be sharp. They actually seem to correlate with something on the seafloor. These are magnetic anomaly orientations. And you can see there's a pretty substantial difference in the fabric of the seafloor that is going down. And so this came from the Kula Pacific Spreading Center. This came from the Farallon Pacific, and this came from Vancouver Pacific. So this is a previous little plate fragment. Basically, the transition in this particular case between wide locked zone and creeping zone almost matches exactly in space the transitional area in the fabric of the seafloor. And this is actually something that Donna, who should be smiling here, proposed. She actually looked at seismic lines across here, and Peter showed that way back on the first day. What he showed from her result is that the development of bending faults at the outer rise is different depending on whether the orientation of the fabric of the seafloor is more or less parallel to the trench or more or less perpendicular to the trench. And the hydration is also different. And you can see this, there's distinctive differences in the seismic velocities of what's going down. So it looks like in this particular case that there's a strong correlation between changes in the downgoing plate and changes in the seismogenic zone response. Yes, we had a question here.
So can you go back to the coupling model? I wonder how well is the down dip end get constrained. I see in the data that most of the interseismic vertical motion is downward.
Yeah.
Does that mean that the coupled area should extend deeper than what you showed here?
So that's a good question. So we see a long wavelength vertical signal that we can't explain with any variation of this subduction related model on the order of 2 or 3 millimeters per year. So, I think it's probably a glacial isostatic adjustment signal, but we can't perfectly fit the vertical. So there's a mismatch between the vertical and the horizontal. If we go back to the data, which is a few slides back, yeah, this shows the data. So this sort of magnitude of subsidence is something that we actually see over a broad region. And we see it whether the plate interface is mostly locked or mostly creeping. So it's not a plate interface effect. But we haven't been able to come up with a model to what it, other than having it be a residual. So, at the moment, our model underpredicts this subsidence as well. That probably indicates that our plate geometry is a little bit wrong. We used slab 1.0 in this case. And so one of the problems we have in this sort of model is from seismology, you get a really good idea of where the slab is at intermediate depths. But unless you have shallow thrust earthquakes, you don't actually get a good idea of where the plate boundary is at shallow depth. And it's the geometry at shallow depth that matters for our case. So in this case, we base the models based on the horizontal data.
Well, one other question is your models in all the areas there show the coupling increasing up dip.
Yeah.
And is that well constrained?
Good question, yes. So actually, it reminds me, I didn't actually quite get how well constrained is the down dip end, which was also part of the previous question. So let me address that now. It's pretty well constrained, except that you can make it abrupt or gradual. As long as you put the center of the zone in about the right place, the fit to the data is very similar. So we don't have a way of telling of whether the coupling distribution goes like a boxcar or goes more gradually. But we can constrain the center of that distribution reasonably well. The up dip part, we actually assumed in this inversion that the coupling fraction can only decrease with depth. That is, we basically assumed that whatever was happening out at the trench, it became less coupled, or less, the slip deficit becomes smaller with depth. The reason for that is we have almost no ability to resolve what happens at the trench. And so that's actually something that you should apply every time you see anybody's model, unless they've got data sitting out there by the trench. You don't know what's happening out by the trench. And so we could take this outermost, shallowest part, basically say this is creeping, and it wouldn't change the data at all. So the only way we get that is by making measurements out by the trench, which usually means beneath the ocean.
Actually, there's a question over there before me. Oh, okay. I was wondering, so you assume you have a plate interface, and I guess that's prescribed, and then also the plate velocity is constant everywhere.
Yeah.
Does it matter if the downgoing plate is also deforming?
Yeah, so we assume we prescribed a plate interface. We're in the process of trying to vary the plate interface to see if we can actually better explain some of the vertical-horizontal mismatch. But we prescribed the plate interface and we prescribed the plate velocity. So it would matter if the plate, if the downgoing plate is deforming at a rate that is substantial, which would have to be millimeters per year. But if it was, and we didn't account for that, that would bias our results. So we are sensitive to deformation of the overriding plate. We only, however, only in kind of the depth range that we care about, which would be maybe from the trench down to 40 kilometers.
And which way would that bias your results? Would you then underpredict?
Let's see. So if let's suppose that let's suppose the downgoing plate was under very rapid extension, even beneath the seismogenic zone. If that was the case, then the slip on the interface would be smaller than the plate motion rate, because some of it would be taken up by extension of the downgoing plate. In that case, we would, let's see, we would overestimate the slip deficit on the interface in that case.
Thanks.
Mm-hmm. Yeah, Claudio is the next.
Yeah, very, very interesting. Could you give us some more insight in the long-term kind of feature? Because of course the fabric in the ocean is a long-term feature, but the seismicity can be a short-term one, so cyclicity and
Right. So, so Donna's hypothesis on the seafloor fabric was that the seafloor fabric was related to essentially the extent of extensional faulting from the outer rise, which then meant a difference in hydration and a difference in the amount of water going down. And so at least in this particular case, it actually seems to correlate quite well with the seismogenic zone variations. Now, exactly how that works, whether it's a matter of roughness or a matter of fluid pressure and so on, it still probably needs to be, there's still multiple interpretations I think you could get between the correlation and the ultimate cause. Whoops, I did not mean to advance. But I think Susan is going to show you a case where there seems to be perhaps a correlation between what's happening on the upper plate and the seismogenic zone. So it is not, I would say, absolutely true everywhere that it's the lower plate that dominates. So there could be variations on upper plate or lower plate that have impacts on the extent of the seismogenic zone. So I think in New Zealand and Japan, for example, it's been argued in the other direction, that it's upper plate control, perhaps in some cases related to how easily fluids can get up into the upper plate.
Yeah, but this would imply that this part will never get strongly
controlled. Yeah. So then the other question is how long, we have data for 20 years that shows this is what happens for 20 years. How do we go to 100,000 years for this, right? So that's a good question, and we don't know fully the answer to that. What we do know in the case of Alaska, let me back up a little bit here to here. What we do know in the case of Alaska is that this pattern of locked zones matches at least more than a century of great earthquakes and where the release is in great earthquakes. So in the 1964 zone, we have two gigantic asperities and a zone in between that had very little slip. We see two big locked regions in a zone that's largely unlocked. This boundary over here at least this boundary over here, this transition from locked to creeping matches the seismogenic behavior, again, of the last century. So we have, I think, reason to believe that to first order, these patterns at least last for multiple earthquake cycles. But I don't think we have any way to know very well whether they last for 100,000 years or a much longer period of time.
Jeff?
Yes?
How is faulting in the overriding plate being accommodated into these models?
Okay, this particular case it is not, except for the block motion. Let's see what. Let me go back here. Okay, so for the most part, it is not except for the block motion or for essentially slip partitioning, where we have strike-slip faults that are allowing things to move. So one thing that becomes very, very important in the Western Aleutians is slip partitioning of the oblique subduction. So that's accounted for. However, for example, if we have observations of slip on splay faults co-seismically here in this region, and we are basically assuming at the moment that those splay faults are not doing anything between earthquakes, that they are sitting there. That assumption is reasonable if you have a geometry like this. If you have a locked megathrust, which is not slipping, and a splay fault which soles into that, as long as it's entirely within the locked zone, there isn't necessarily any reason for there to be any creep in between earthquakes on that splay fault. So if some part of that splay fault is creeping, we should see strain associated with that. If it's not, it's almost invisible in between earthquakes. So the geometry gets a little bit, you can have certain kinds of geometries that look the same in the interseismic period. And one of those is a shallow splay fault. We probably can't, in general, see those geodetically, unless some part of that fault is creeping. And then if it is, we should see some localized strain associated with it. Yeah,
so I wanted to make a comment related to this variation in where you have outer rise faulting and where you don't. Mm-hmm. Because in this particular place where you have the fabric coming in at a high angle, you do not have outer rise faults forming. But in other places, outer rise faults form just they just don't take advantage of that fabric. They just break right through. So it's a really interesting feature of this particular subduction zone that somehow the bending of the plate in that particular area is not sufficient to actually break and create new faults. And that is telling you something about how the bending of the fault is actually being modified probably by the overriding plate, because you don't have enough stress to actually fracture and create new faults.
Right. If it was a sharper bend, perhaps.
Perhaps, right. Yeah.
Then it might break.
In Tonga, for example, your fabric is perpendicular to the trench, and you have huge scarps with huge faults across.
But it's got a pretty sharp bend to it. Perhaps. So so I think looking at that's right. That may be modulated then by what the deeper slab is doing, and so it's all of the parts of the system kind of work together. Yeah, I agree. Okay, so let me try to move on. Let me just mention again, these long strike variations are, again, very, very common. This is an update of the New Zealand figure. The gray scale is now the slip deficit on the megathrust. These colored blobs are the slip areas in slow slip events, which I'll talk about in a minute. And basically, the slow slip events always kind of hug the down dip end of the locked zone. Even when that occurs at very shallow depth up here in the Gisborne area and much deeper in southern North Island.
Jeff, you have about 5 minutes maybe?
Yeah. So, well, there were introductions. Come on. Give me another 5. All right. So let's look at, is the shallow
benefit of all these
megathrust locked?
questions.
I know. Well, we've had lots of good questions. So is the shallow megathrust locked? In most cases, we don't know, actually, geodetically, because the only way we know is by having measurements out over the trench. This was actually done in the Peru trench. These little red triangles are seafloor GPS acoustic sites. So acoustic transponders on the seafloor positioned relative to a buoy on the surface, position the buoy with GPS, and you can basically get centimeter level, maybe 2 centimeter level positioning of the seafloor. And they repeated these measurements, and the different colored curves are different models, and they differ by where the up dip limit of the locked zone is. And so, for example, a variety of ones, but the key point here is all of these models fit the data on land about equally well. But only the models that have, in this case, the fault locked all the way out to the trench fit the seafloor data. So this suggests, at least in Peru, in this one place, that the megathrust is basically locked all the way out to the trench. Another place where we can actually infer that is from a continental megathrust, and that's Nepal. So this is the recent Nepal earthquake. It ruptured at depth. It did not rupture to the surface. However, we also know from GPS measurements that there's no interseismic creep at the surface either. So the shallow part of this system did not break in this earthquake. And it may be a case where this more moderate earthquake happens every few hundred years, and every several hundred years you actually get a big one that ruptures all the way to the surface. So, so it may well be that in many cases that the shallow megathrust is actually locked. And I'm going to go out on a limb here and say probably yes. I'm sure there's variation from place to place. But we have reason to believe that it may actually be locked out towards the trench. However, the only way to really test that is with seafloor data. We have to make measurements on the seafloor and do positioning out towards the trench to ever really answer this question. All right, so looks like I'm going to only get as far as slow slip events, but that's okay. I'll talk briefly about slow slip events and then end here. What we see here are, on the left, are 2 sets of vectors. The black ones are the sort of steady interseismic velocities, and then the red ones are the displacements over a particular interval. And what we're seeing here is one of these little blue zones. So the time series here, we'll just look at one. This is the east component. This site, Albert Head, moves eastward, and then it, over a period of a few weeks, moves westward, then eastward steadily, rapidly over a few weeks moves westward, and so on. Each one of these little blue things is a slow slip event. It's basically like an earthquake, except instead of taking seconds or a minute or two, it takes a few weeks. So it involves slip that is fast compared to plate motion, but slow compared to earthquake slip. And these are very common. This is from Joan Gomberg. This is the slip distribution in the colors from one particular large slow slip event in Cascadia. And what you see in the little white circles are the location of the seismic tremors that were associated with that. And Susan's going to talk much more about that process, but there is a seismic signature in many cases to this slow slip. It just doesn't look like an earthquake. We see a little bit about this in Alaska, and what I want to show you is evidence that these slow slip events can be very, very long-lived. So the Cascadia events last a few weeks each, more or less. I'm going to show you evidence for multi-year slow slip events in Alaska. And I think I'm going to skip this part because we're almost out of time. But except to say that the coseismic slip and the after slip and the slow slip overlap each other in one of these zones. So, so here is a time series of a site. We're looking at the north component and the height. The site, when it was first put in, was moving rapidly southward, turned around, started moving to the north. This is the 2002 Denali Fault earthquake, which was pretty far away, but still causes a displacement. There may be, in fact, I think we now know there are a few small slow slip events, and then there's another big multi-year event. So this particular site is very nonlinear. And we're seeing something really dominated by slow slip. You can even see it in the vertical. The site uplifts during the slow slip events and more or less is not uplifting in between the slow slip events. We can locate them, and then we can also see some other characters. So this next slide is a cross-section through this area where we also see long-term slow slip events. And this is just the north component position. You can see these kinks in the time series. It's been detrended based on this interval. And you can see that there's not very many sites from this earlier time period, but their motion is very, very distinctly different than it was in this interval. And it's pretty linear over this time period, at least to the ability we can resolve it with these kinds of data. It turns out this is actually a time period with no slow slip event, and this is a at least 9-year-long slow slip event. And I've only shown you a few of the time series, but if we look at all of the sites and how the velocities change from interval to interval, we can actually constrain where that is. And that basically, this is where that 9-year-long slow slip event is. Again, it's down dip of the locked zone, which is in red here. And but 9 years is a long time for slow slip. Come on. And let me just end here. We'll look at the duration and magnitude. Again, Susan's going to show you where this figure comes from. There's a relationship between duration of slow slip events and seismic moment. And roughly speaking, IDE proposed that there's a roughly linear relation between the duration of slip in a slow slip event and the seismic moment. That's very different than the relationship you see for regular earthquakes. So and then a lot of different places, slow slip events are plotted on here. The multi-year Alaska events actually basically plot along the same curve, but are getting up into things that are, again, multi-year. And the very longest slow slip event we have data for comes from coral observations in Sumatra. It's about a 15-year-long event. So 15 years of slow slip. And again, we see this wide variety. So I think I'll just stop here. I've got some more things in the slides for those who want to look at them. I didn't quite get to one of my favorite post-seismic deformation things, but, well, I guess I took too long on some of the other parts. So we'll open it up to questions.
Too much good stuff. So do we have questions from the students and postdocs? Yeah.
Hi, Jeff. Good talk. I have a question about the split fault. Since you mentioned about the sleep deficit of Alaska, do you have any comments about the sleep deficits of split faults in that region, since we know there are?
Right. So what is observed, or what has been observed for the long term, for the outboard of Prince William Sound, so just off the southern coast of Alaska, there's a whole host of splay faults. They've actually been identified in high-resolution seismic reflection, to some extent, there's some idea of how long each one might have slipped, because there's certain horizons that are datable that you can get a total offset. If you look at those total offsets measured compared to what happened in 1964, where there was as much as 10 meters or so of slip on some of these splays, each splay that we can see only may account for several earthquakes or more. So the current thinking is that probably those splay faults only actually rupture coseismically when there's a large slip on the megathrust. And I mentioned that there's a pretty large long strike variation in slip on the megathrust in 1964. So there's a big asperity and then a gap that has very little slip. The splay faults extend pretty close to that same boundary. So that is, the splay faults seem to stop as clear features on the seafloor when we go from the area that has large seismic slip to the area that doesn't. And that again supports the idea that most of the slip on the splay faults is occurring during large megathrust earthquakes. So at least that's the case for Alaska. I'm not sure if that's always generally true, but that seems to be the case for southern Alaska.
Are there any systematic differences between areas where we see the week-long slow slip events versus these 10-year long events?
So I don't think we understand why they are different durations. New Zealand has some sort of intermediate length things, things that last months. Japan has both short-term ones that last days to weeks and long-term ones that last, in some cases, up to a few years. There does seem perhaps to be a spatial difference and, or a depth difference. And let me come back to this figure. In Japan, the short-term slow slip events that look like the Cascadia ones more or less seem to come from the same place as the band of tremor. And the long-term slow slip events involve slip at shallower depth as well. So there probably is some depth difference in between these longer-term events and the shorter-term events. In Alaska, for the long-term events, the one that's up here, this one we see tremor at the down dip end, but the slip extends well up dip of the tremor. This one we actually don't see tremor, or it hasn't been recognized anyway. If there is tremor, it hasn't been recognized. So there does seem to be some difference in the spatial distribution of slip between the short-term events and the long-term events. So that presumably means some difference in the physical properties. But beyond that, I don't think we actually know. Yeah.
That's sort of a comment that's then a question that's related to it. So for the Peru data you showed, it's still possible that the first 20, 25 kilometers aren't necessarily locked. Yeah.
So for example, right, the red is no slip to all the way from the trench to 40 kilometers. That's no slip from 2 kilometers to 40 kilometers, and I think
that's in depth, though, right?
So that's in depth. So even then, because there's still some gap here, what's the distance? The closest site is about 20 kilometers from the trench. So at some point out right at the trench, even then we start losing resolution. So yeah, so there is still some possibility of a very, very narrow slipping zone, even with this data. And of course, there's an error bar here, so you could get something that has, several kilometers depth probably of dominantly creeping, and you could probably still, pass through the error bar.
So do you think if we had some information on compositional constraints of the 4-arc, and then we usually have a lot of places with really good bathymetry data, we can try to make some inferences about what the locking might be like from looking at the slopes. And like if you for Alaska, for example, there's to the west, I believe, parts that are very flat for long periods and then sudden faults creating very sharp changes in bathymetry. And if, as you go east, there's sections where it's more of a gradual, long sustained slope.
I think you could look at that, and I think that's worth looking at. I don't know. Yeah, I don't know exactly if you would find a super strong correlation or not, but I think that's worth looking at, because in the time period that we've actually started to know something about these slip variations, I don't think those kinds of careful studies have been done for the most part. So I think it's worth looking at.
Other questions from students and postdocs? Okay, we'll open it up. I know Donna was very anxious to give a question.
I wanted to ask you about, you showed a result a couple years ago, I think at Lamont, where you could see from continuous data that the down dip edge of the locked zone varied through time. I can't remember if it was over months or years. And so I was just curious, both Alaska and globally, how much kind of temporal variation there was in the locked zone, and on what time scales and over what distances. So sorry.
Okay, so let's look at this particular figure. So this is the time period on the right where there's no slow slip event, and this is the time period where there is a slow slip event. So you could basically difference these two. And so if we're looking at this part of the Kenai Peninsula, sort of the midpoint between fully locked and zero is somewhere out here, offshore, whereas it's moved somewhat inland here. So there is variation in this case at the level of tens of kilometers in the width, or let's say in the lateral position of that down dip end. This is a pretty shallow dipping slab, so it's maybe 5-degree dip or something like that, or a 7-degree dip at this. So it's not a huge depth change, actually. But yeah, so we do see, and yeah, this particular this particular figure, we can't do the same analysis up here because the time windows we chose don't line up with the time windows of that other slow slip event. They were chosen for here. So we do see variations on the order of tens of kilometers in this very, very shallow dipping case, which amounts to a few kilometers in depth. But we haven't yet seen examples of, for example, here, there's a really big difference in the width of the lock zone. And again, with the lack of resolution out by the trench, I mean, you could change this whole thing to creeping and it would barely change the data. So it's poorly resolved that there's any lock zone at all. But the down dip end of the lock zone comes way in here. We've never seen anything that's hundreds of kilometers variation. And we do see that so I think we see some first order changes in the width of the lock zone at the several tens to even into the hundreds of kilometers in some cases in Alaska, which I suspect is long-term or relatively long-term. And then these big slow slip events dynamically change things at the tens of kilometers laterally and maybe a few kilometers in depth. So there's definitely a zone in here which is quite dynamic, and where what you measure over a period of a few years may or may not even be representative of a decadal scale.
Okay. You showed an interesting plot by Ida and others, a correlation between the duration of moment release and the duration of slow slip events. I'm curious if there's similar studies how the moment release is related, is or is not related to the rate of slow slip.
Okay, so let's see. Yes, that has been looked at. So, so this is basically, right, so this is duration versus moment. Moment more or less is slip in this case. So duration versus slip. There was a paper done several years ago by Lovelace and Mead that took this relationship as well as some other assumptions, and essentially what they came about is that the average rate of slow slip should decrease as the duration of the event gets longer. In order to match this duration moment law, these short ones involve somewhat faster slip than the long ones do. So there is a systematic variation between fast but short-lived slip and slow, long-lived slip. And what's interesting about that is if you get up to the decadal scale, the slip rate that they would infer from their scaling relationship gets down to centimeters per year. So that's getting down to plate motion rates, which is kind of intriguing. But yes, there is a difference, and I think the shorter-lived events, although they're still much, much slower than a regular earthquake, have faster slip rates than the long-lived events. And I think we see that in the observations systematically as well.
I have a short request of you and other speakers. A frontier area is actually connecting all these exciting things that are happening around from the trench to the forearc to what's happening at the volcanic arc. Mm-hmm. Please put the volcanoes on your figures. It would really help to orient us and have us start thinking about how the arc is responding to these differences in deformation. So please include the volcanoes.
Okay,
as long as you include the earthquakes.
I did not include them on the
you have to include the earthquakes.
We have Thorsten, if there's...
Yeah, this will be the last question then from Thorsten.
I was just wondering if you had a feeling for this, how anomalous and how possibly related to the megathrust rupture was this multi-year transient into Hoku-Oki, where there was this multi-year slow slip event that really seems to have very similar spatial extent to the later rupture. Right. Is that just part of the zoo, or is this maybe actually related to the megathrust rupture?
If people haven't seen this, this paper, it was really quite an interesting result from Paul Siegel's group. What they actually observed in Japan in the roughly decade or so before Tohoku was a systematic change in the deformation pattern. And so I think it may be part of the zoo of these long-term slow slip events. And so again, that sort of points to down dip of the main locked zone being something that is very changeable in its behavior from year to year. I don't think there's anywhere else we have seen something on the scale of what they observed prior to Tohoku. I mean, there are shorter term variations maybe in South America, but those were associated with a vigorous foreshock sequence, right? But there also aren't that many places where we had really, really great data before a big megathrust earthquake. So it does again look like certainly at the kilometers in depth extent, at the down dip of the main locked zone is really quite dynamic, and I suspect that what they observed is part of the zoo of these slow events. I'm not actually sure where it would plot on here. The duration would be somewhere up here, but I don't remember exactly what magnitude they would.
Okay, I think we'll have to go to the coffee break. Thanks, Jeff. That was great.